Okay, so we have looked at a number of different methods for solving differential equations. So we have seen how if you can somehow get the general solution for a homogeneous differential equation, if you even if you put some some function on the right hand side and make it an inhomogeneous equation, there is a way to solve this problem. And two methods we considered uh, you know, to work out this kind of a problem was, one of them was the variation of parameters of method, and the other one was the green function method, right? So all of this is possible only if you have some a priori way of getting a general solution for the homogeneous differential equation. So it turns out that even very simple looking homogeneous differential equations cannot be solved in closed form, right? So therefore we discuss a method which is called the power series method in this lecture, which will enable us to find when possible a power series solutions for homogeneous differential equations. So in this lecture we will with the help of a very familiar example, we will illustrate how this method plays out. Okay, yeah, so like we said, in general, homogeneous differential equations, if you can find a general solution by some method, right, you have access to inhomogeneous differential equations as well, as we have seen. But even the homogeneous differential equation itself can be a hard problem many a time. And so the kind of differential equation we are interested in working out is this is the following, which is a naught of x, some function of x sits there, g squared y by dx squared plus a1 of x dy by dx plus a2 of x y is equal to 0. So it's homogeneous because the right hand side is 0. But the difficulty comes because a0, a1 and a2 are functions of x. If they had been constants, then of course we know how to solve this problem. It's only when you make them to be functions, sometimes even very simple functions, render this differential equation a hard problem. So in general there won't be closed form solutions for this kind of a differential equation, but the technique that we will describe here today involves making an onsorts of this infinite series form. So we ask the question, if suppose there is an infinite series, right? So we know that functions have Taylor series expansions, right, which are valid in some interval and so on, right? So at this point we will not go into discussions of convergence and so on, right? So just suppose there is a Taylor series, like expansion of this kind of power series expansion, which is a solution to this kind of a differential equation. How can we work such a series out if it exists, right? So that's the type of question we will address in this lecture with the help of a familiar example. So what we will do is we will look at the quantum harmonic oscillator, right? So we wish to find the eigenfunctions of the one-dimensional harmonic oscillator problem. So the potential we have is v of x is equal to half m omega squared x squared, and our goal is to solve the Schrodinger equation corresponding to this potential, right? It's a very familiar potential, and this problem has been surely most of you have encountered this problem, and probably you have seen a clever algebraic approach, operator approach to solve for this. And but there is also a differential equation way of solving for this this problem, which is our which is the approach we will describe in detail, right? So this is described, for example, in Griffith's textbook, right? So here it's like a textbook example of a differential equation and how we can apply the power series method to work the solution out, right? So the potential that we are considering here, the harmonic oscillator potential, is is of vital importance. It appears in all kinds of contexts. So sometimes it may not be exactly of this form x squared, but the idea is that lots of potentials are restoring in nature, and so the simplest approximation for a a stable equilibrium setup is to make it is to take the quadratic potential, and that's why this is of such great importance to understand this problem. So for sure, the quantum harmonic oscillator, the harmonic oscillator itself, we have seen, the classical harmonic oscillator itself, we spent quite some time about from the point of view of differential equations. But now we see that the Schrodinger equation applied to the quantum harmonic oscillator also leads us to a very important problem. So this time around, it will tell us about, uh, uh, how to use the power series method, right? So it is there is no doubt that this problem is of great importance, and it appears in all kinds of contexts. So it is good to understand the solution well. Okay, so the first step is to non-dimensionalize this, right? So we start with the differential equation, which is the Schrodinger equation, which is h psi is equal to E psi. So what we are doing is here solving for the time independent Schrodinger equation, right, from which you can also solve the time dependent Schrodinger equation. So time independent Schrodinger equation is h psi is equal to E psi, and h in this case is given by minus h cross squared by 2m d squared by dx squared plus the potential, which is half m omega squared x squared. So this is the differential equation which we need to solve. So the first step is to non-dimensionalize this, so that you remove, in some sense you are removing all the physics away and treating it as a pure mathematical problem, and then you put the physics back in the end. So we use, this non-dimensionalization. So natural, units for length here you can check is 1 over square root of m omega by h cross. So what you do is wherever you have x, you replace it by, x divided by this quantity, and where you have e, you replace it by e divided by h cross omega by 2, right? So I mean, you could use some other variable and so on, right? But it's convenient for us to just, work with x itself, right? So now with the understanding that the x that we are dealing with here is a non-dimensional x, and the e that we are dealing with here is a non-dimensional e. So you see, this differential equation with all these constants and everything, just becomes a simpler differential equation, because you have, pulled away all these constants. So you have d squared psi by dx squared in these new units plus e minus x squared is times psi equal to 0, right? So you have this minus sign, so this object goes to the right hand side, and then you have this becomes a minus sign, so e is positive here. So now you see that this equation is evidently in the form, the form that we first described. So there is a second order, this second order derivative. First order derivative is missing, so there is a constant associated with the first one, and the only function that appears is just e minus x squared, right? So we would of course know how to solve this problem if there were no x squared. If it were just e, of course that's the simple harmonic oscillator problem, the classical harmonic oscillator problem, right? So it's I mean, it's then you should not think of it as a wave function then, right? It's a familiar problem from classical harmonic oscillator if there were no x squared, but x squared is present, right, which is the potential energy term. And this is, it's surprising that, such a simple change to one of these coefficients makes it such a difficult problem. It's no longer possible to write its solution down in a closed form way, and so we must find recourse to a power series solution, right? So but before we do that, it's useful to bring in some intuition, some physical intuition here. So and look at what happens for very large x, right? So this is a wave function that we are looking for, and wave function must satisfy certain properties, right? So we can massage this differential equation into a slightly different form, while keeping it completely general in this new form, but it's a more convenient form for the purpose of this power series solution, right? So the idea is to look at what happens to this differential equation when x becomes very large, either positive or negative. You see, there is this x squared will make sure that this term e minus x squared will become basically minus x squared. X squared will dominate over e, and so you are left with just the differential equation approximately becomes d squared psi by dx squared is approximately equal to just x squared psi, right? So if you can find a solution for this, we can look at what these wave functions will be like at large x, positive and negative. And so a little bit of guesswork, we can figure out that the solution should be of this form, e to the minus x squared by 2, right? So the way to see this is that if if you take a single derivative, you would want an x to be a factor of x to come in, and a second derivative should bring in another factor of x. So then you start guessing that maybe something like e to the x squared will work out. Then you say, okay, let's say maybe e to the alpha times x squared, and then you try to fix the alpha, which will turn out to be either plus half or minus half in this case, right? So it's a kind of a guesswork game. And then you argue that, suppose we make this as a an ansatz for this differential equation. It's an approximate differential equation, and so this turns out to be an approximate solution, which becomes a good solution for large x, right? So a way to check this is to just differentiate it. So if you do d psi by dx, then you get minus ax e to the minus x squared by 2 plus bx e to the x squared by 2. If you differentiate it again, then you get ax squared e to the minus x squared by 2 plus bx squared e to the x squared by 2. The first two are basically like what you're interested in, but you also have these other two terms, minus a e to the minus x squared by 2 plus b e to the x squared by 2. These come from differentiating with respect to x in each of these terms. And so the argument is that, for large x, since you have these x squareds sitting here in the first two terms, these terms are going to completely dominate over the third and the fourth. So you can ignore these two terms, right? The last two terms you can ignore, well, because they're small in comparison to the first two. And then you also observe that the first two terms are really the same as x squared times psi. So indeed, for large x, this is an approximate solution for your problem. So in other words, in fact, you have e to the minus x squared by 2 and e to the x squared by 2 are both approximations for this solutions of a differential for large x. Now comes the physical argument. So we argue that we are not interested in solutions whose asymptotic behavior is e to the x squared by 2, because then these are solutions which will become very large for large x, and so they will not be normalizable solutions, right? So since we are interested in wave functions, eigenfunctions for these for the harmonic oscillator problem, so for it to have physical meaning, we know from quantum mechanics that these eigenfunctions must be normalizable. So this requirement for normalization means that we are not interested in these solutions which fall off as e to the x squared by 2, but rather we would be interested in solutions which have this e to the minus x squared by 2, right? So therefore what we do is we look for solutions of this form. So instead of just directly searching for the solution for the differential equation for psi of x, we say that psi of x itself will be some function times e to the minus x squared by 2, which is a kind of a peeling off operation which one does. You say that, okay, there is this, we want e to the minus x squared by 2, this is a desirable type of solution, so why don't we explicitly put this in by hand, right? You could have also done it without doing this, but it turns out that the differential equation that you get in H is a convenient differential equation which we will be able to relate to a standard differential equation. So that's why this is a useful thing to do, right? So we will see as we go along in this lecture how this differential equation in H instead of differential equation in psi is a convenient differential equation to work with. Okay, so what we do is, so now we have to work out first of all what the differential equation for H is, and then solve it using the power series approach. So at this point it's completely general, right? So it's like all we have done is we have used some physical intuition to to think of solutions which have a plausible form, and then we are looking for solutions of that form. And in fact we'll look at a different differential equation, but actually so far we have not done any approximation. There is no loss in there is no there's no nothing fundamentally that has been lost so far. It has it's like a transformation. Instead of solving one problem, you're solving another problem which which can get back you the solution to the first problem itself, right? So what is that new problem? The transformation is obtained by first doing these two derivatives. So d psi by dx is dh by dx minus x times h, the whole times e to the minus x squared by 2. So that's the thing about these factors of e to the minus x squared by 2. If you take a derivative, you still leave such factors around after every differentiation. And so you can pull out this entire factor. When you take another derivative, once again you get either d squared h by dx squared, or if you're differentiating the second term, if you differentiate with respect to h, so then you get x times dh by dx e to the minus x squared by 2. But you could have also done it with the first term when you are differentiating with the second one, which will give you minus x times dh by dx e to the minus x squared. So you collect both of these, so you get minus 2x dh by dx, and then you also have this x squared, which comes about when you take a derivative of this guy e to the minus x squared by 2 for the second term. And then you also have a minus minus h. So if you take a derivative with respect to x, so that will give you just h times e to the minus x squared by 2. If you take a derivative with respect to e to the minus x squared by 2, that will give you x, that will become x squared minus 1, right? So you can convince yourself that indeed this is the first derivative and second derivative. Then you go ahead and plug back these quantities into the original differential equation, right, which is this one. So d squared psi by dx squared plus e minus x squared the whole times psi. So then we see that you still have these factors which are sticking around, which you can cancel, right, because this needs to hold for all values of x. So indeed d squared h by, you get a simplified differential equation in x, which is also second order in a differential equation in h, which is also a second order differential equation in h. So we have d squared h by dx squared minus 2x dh by dx plus e minus 1 times h equals 0. So this x squared will cancel with this minus x squared, and you're just left with e minus 1 times h is equal to 0. So finally we are ready to make our power series onsorts. So we seek solutions of this form. H of x is equal to summation over j aj x to the j, right? So we assume that this is a convergent series, and it has all these nice properties, so that you can take you can take derivatives of this function, and then term by term you can differentiate, term by term you can the convergence remains unharmed, right? So we assume this at this point, right? We're not going into a detailed discussion of these convergence issues at this point, because we want to just illustrate how the technique works. So assuming that this holds, so you have dh by dx is equal to j times aj x to the j minus 1. So what we want to do is make this onsorts and plug this into your differential equation. So we will actually have to work with x times dh by dx. So we will work that out in a moment. We leave this differential series expansion for dh by dx as it is. But if we differentiate a second time, we get d squared h by dx squared is equal to summation over j times j minus 1 times aj times x to the j minus 2. Now we observe that the first term and the second term are really 0. J equal to 0 will cause the first term to be 0. J equal to 1 will cause this factor will cause it to be the second term to be 0. So for all practical purposes, this summation actually runs from j equal to 2 to infinity, and then we can make the change of variable. J minus 2 is equal to some k. So then in place of j minus 2 you'll write k, and in place of j you'll write k plus 2. In place of j minus 1 you will write j equal to k plus 2, so it will become k plus 1, and this one will become k plus 2. And then you argue that, oh, it's just a dummy variable which is getting summed. Instead of k running from 2 to infinity, you can I mean you had j running from 2 to infinity, and so k will run from 0 to infinity, but you say k is in place of k you might as well just call it j again, and so then you have j going from 0 to infinity, j plus 1 times j plus 2 times aj plus 2 times x to the j, right? So we want to bring this, each of these terms is a summation, but they all should be x to the j, right? That's the idea. And then of course, since dh by dx has this factor x in this differential equation, we can just write it as x times dh by dx is equal to summation over j times aj times x to the j, right? So now we have expressions, series expressions for h of x in the second term and the third term. We just plug this in, and now we have summation over j plus 1 times j plus 2 times j plus 2 minus 2j aj plus e minus 1 times aj all of this multiplied with x to the j equal to 0. Now we argue that if this has to be 0 for any value of x, so this has to be in fact 0 term by term. So every coefficient must in fact be 0. So we get j plus 1 times j plus 2 times aj plus 2 minus 2j aj plus e minus 1 aj equal to 0. So this is a very important result. So because what it does is it gives us a recursion relation. It tells us that we are looking for a power series in which the coefficients are related by this relation, right? So if you know aj, then it tells you how to go to aj plus 2, right? And so what it means is, so you see that this factor is in terms of j and e. E is your the energy of your system, and what it tells you is these coefficients relate aj to aj plus 2. So in fact, if by some means if you fixed a0 and a1, so a0 will fix for you a2, but if you know a2 you know a4, if you know a4 you know a6, because of the same rule can be applied repeatedly. And likewise, if you know a1, it will give you a3, it will then give you a5, and in turn a7, and so on, right? So all the odd coefficients are fixed if you know a1, and all the even coefficients are fixed if you know a0. So in fact, it's not a surprise that this happens, because after all we are working with a second order differential equation which contains two free parameters. So it turns out that all the information that is there in the second order differential equation is compressed into this recursion relation involving two free constants. If you have two free constants, you have you have the full solution, right? So in other words, we have managed to show that h of x is equal to a0. I'm just writing out the first few terms, times 1 plus 1 minus e by 2 if you have the energy, and if you fix a0 and a1, you have the solution, a1 minus e divided by 2 times x squared plus 5 minus e by 12 times 1 minus e divided by 2 times x to the 4. So you have two of these factors appearing here, because one comes from here, it's just e1 minus e by 2, because a2 after all is related, a4 is related in terms of a2, so you have to put in a2 and this stuff. And likewise, if you work out the next one, that will have three such factors, this whole stuff times another factor. And likewise, you see a1, if you fix a1, that will give you x, that's the coefficient corresponding to x. Then you have plus 3 minus e divided by 6 times x cube plus 7 minus e by 20 times 3 minus e by 6x to the 5, and so on, right? So I've just explicitly written down the first few terms using this recursion relation to show you how this operates in practice. So as far as a differential equation is concerned, so it seems like we have got the solution, right? For this h, if we know h, we also know psi, right? But there is some more physics we have to put into this to make it a meaningful solution. We are not only interested in a solution for this problem, but we are interested in finding a meaningful solution for this differential equation, for the Schrodinger equation, right? So in order to see what this means, we have this infinite power series. Does it make sense at all? So let's see what happens to this recursion relation when j becomes very large. So when j becomes very large, you see that 2j plus 1 minus e, you can replace this stuff with just 2j, because j is the only thing which is very large and the others can be ignored. So in place of 2j plus some minor stuff, you can just rewrite this 2j, and likewise the denominators, you can replace j plus 1 times j plus 2 by just j squared. So in the end, you have 2j divided by j squared, which is just 2 by j. So basically this recursion relation for large j will just become aj plus 2 is approximately equal to 2 by j times aj. So some more thought reveals that in fact we can write a closed form expression for aj in term, because of this this property that aj plus 2 goes as aj divided by j, and there's a factor of 2 involved as well. So in fact there is a factorial connection which comes to mind, because there is this the relationship between a certain number and 2 more than that are related by a factor involving that number itself. So you have to play with this idea that there might be a factorial involved, and you have to work out exactly what the solution is, and then you make a guess that in fact if you try aj is approximately equal to some constant divided by j by 2 factorial, right? So this comes because of this 2 involved here. and then it's going to be a solution to this, right? So the way to see this is to just calculate what happens to aj plus 2. So aj plus 2 will become c divided by j plus 2 divided by 2 factorial, but j plus 2 divided by 2 is the same as j by 2 plus 1, so there's a factorial. So that is, so you can pull out one of these factors, 1 over j by 2 plus 1 times c by j by 2 the whole factorial. But c by j by 2 the whole factorial is actually nothing but the solution we have for aj, and j by 2 plus 1, since we are going to assume that j is large, you can replace j by 2 plus 1 with just j by 2. So you see that this is approximately equal to just 2 by j times aj. So aj plus 2 is indeed for large j approximately like 2 by j times aj, if you choose aj to be of this form. It's like some constant divided by j by 2 factorial. So if we take this to be our solution, right, so that means for large x our solution has this form, h of x is summation over x summation over x to the j divided by j by 2 factorial, which is the same as saying it's a summation over x to the 2j divided by j factorial, which will work out approximately to be some constant times e to the x squared, right? So this is just a sort of a rough calculation we are doing for what happens to this function h of x for large x, if by looking at aj for large j. Now this will lead us to the solution e to the x squared, which is actually the undesirable solution. Why? Because if h of x goes as e to the x squared, then we do this sort of peeling off operation we had done, because ultimately we are interested in psi of x. So psi of x will be h of x times e to the minus x squared by 2. So if you put these two together, you will get psi of x will go as approximately c times e to the x squared by 2, right? So which is actually the solution we found undesirable. We did not want this type of a solution because it's going to be not normalizable, right? So it seems like no matter how you choose your a0 and a1, if the series keeps on going all the way to infinity, if you make j to be arbitrarily large, it's going to give us a solution which we don't want. So the only way to avoid this, it turns out, is to forcefully truncate the series, right? So you have to choose your energy E in such a way, if your energy were such that at some point this series were to terminate, and then if we cleverly chose one of these coefficients, a0 or a1, to be 0, right? So we have an odd sequence and an even sequence. If you choose a0 to be 0, then you are only left with a1, a3, so on. And let's say, so if a0 is 0, a2 is 0, a4 is 0, all of these are 0. But on the other hand, let's say you start with a1 and then it goes to a3 and then it goes to a5, and then there is a certain n at which, let's say that an plus 2 is going to go to 0. If by some means you can arrange that, right, by choosing your E appropriately, then you're guaranteed that you'll get a solution which doesn't become, which doesn't go to this type of a solution, right? Let's see what happens if we do this. So how do we force this this power series to truncate beyond a particular n, right? So we choose our energy E to be 2n plus 1. So we see that here, if there exists a j which equal to n, we'll call it n. When j becomes n, so you have 2n plus 1 minus E. So if 2n plus 1 is actually equal to E, then we will get an plus 2 is 0. Once you get an plus 2 is 0, everybody after that is also 0, right? We choose one of these coefficients, either a0 or a1, to be 0, and we also choose our energy E to be 2n plus 1, right, such that n can take value 0, 1, 2, and so on, which we already see that this is how the quantization condition of for energies of the harmonic oscillator works out, right? So this is some very obscure way of obtaining this quantization condition, which comes from putting in these physical requirements on the solution of a differential equation, which we have obtained by power series methods, right? So if you do the operator algebra method, you have another way of obtaining this quantization condition. But from the differential equation point of view, it appears, because of this demand that the solutions obtained to this for this differential equation be meaningful, right? In particular, we don't like solutions which become very large for large x, and so there's normalization. That's the requirement which forces energy to take only certain values, right? So when we restrict E in this manner, so the differential equation also changes. So we see that we started with this d squared h by dx squared minus 2x dh by dx. Then we had for this differential equation we had plus e minus 1 times h equal to 0. But e minus 1 will just become 2n, right, in these units. So the differential equation just becomes plus 2n h equal to 0, right? And the solutions when you do this, are polynomials, right? So aj plus 2, so which we fix n to be 0, 1, 2 and so on, and then we get these polynomials. In other words, these power series don't go all the way to infinity, they are polynomials. So definitely there's no difficulty with convergence and so on, right? So for this particular very precise choice that we make, they become polynomials, which are extremely well behaved functions, and they are meaningful for all values of x and so on. And they have exactly the properties that we demand for the wave function, right? So they will yield properties for the wave function, which is connected very closely to h of x. So if we can find h, we can also find psi, which is just with the help of a factor. Now, so here what I have done is, so the recursion relation also has changed, right? So in place of e, I have put 2n plus 1. So the recursion relation here, in place of e, I have put 2n plus 1. So 1 will cancel, and then I will be left with just 2 times j minus n, or which can be written as minus 2 times n minus j divided by j plus 1 times j plus 2. This whole stuff times aj. So this is the solution for this differential equation, and here the solution is a polynomial solution for this, right? So the set of polynomials which are obtained for different values of n, right? So this is a well-known set of polynomials. So these go by the name of Hamid polynomials, and they have some convention which gives them certain special factors, right? So I have just put in those factors involving some factorial n, and you can look up this, right? So if you use these Hermite polynomials, right, so which goes back to this differential equation and whose recursion relation is this, and you use a suitable set of factors which depends on n in a very special way. I'm not giving you that formula here, but probably there will be more extensive discussion about orthogonal polynomials and so on in the next part of this course, right? So in any case, so this is like from a differential equation point of view, using the power series method, we see that for the harmonic oscillator problem, we will get Hamid polynomials which are the power series truncates beyond a certain point, and it becomes in fact a set of polynomials. The first few polynomials are just 1, 2x, 4x squared minus 2, 8x cubed minus 12x, 16x to the 4 minus 14x, 48x squared plus 12, and so on, right? So these are all polynomials which you can look up from some tables, for example, or you will see many properties of this in a discussion on orthogonal polynomials. But the key point here is that these are alternately odd and even polynomials, right? Which is what you expect, because you have one of these, either a0 or a1, to be 0, and the other one is non-zero, and then it truncates at a certain finite value, and it keeps on increasing. So the first one has just one term, second also has only one term, then third one will have two. h2 has 2, h3 has again 2, and h4 has 3, and so on, right? So this has to do with how the series truncates at the nth position. So in the original units, so the quantization condition, this is the form in which we have seen it. Most of us have seen this relation, En is equal to n plus half h cross omega, right? So we are told in more elementary courses that there is a quantization which happens for the harmonic oscillator, and this is the formula for it, and that n can take value 0, 1, 2, and so on. So the ground state energy is just half h cross omega, and so on. And the wave function of the original Schrodinger equation itself also can be written down in terms of these Hamid polynomials. So you see there are these factor of 1 over square root of 2 to the n and factorial. This comes in because of the convention that is followed for Hamid polynomials. And then we have plugged in the original units, therefore you have all these factors of m omega divided by pi h cross the whole to the power 1/4, and the polynomial hn is not of just x, but you also have this factor that you have to use because you have this original units, square root of m omega divided by h cross, and then you have e to the minus m omega by 2h cross times x squared. So in this lecture we managed to work out the solution for the Schrodinger equation problem, or the differential equation coming from the Schrodinger equation of the one-dimensional quantum harmonic oscillator problem, and we use this problem to illustrate how the power series method works out. That's all for this lecture. Thank you.